Now we know that based on the assumption that we make so far, the gas particles are in constant random motion. They are going to collide with the surface there. And every time, well, they're going to collide with the wall of the container there. Every time the collision happens, there's a small amount of force exerted. Now, it's a large collection of huge number of particles there. So when the gas molecules are moving in random directions, they are constantly colliding with the wall of the container. As a result, you have pressure exerted. So when you have a certain amount of gas trapped inside a particular container, there's always a pressure associated to it. Okay, how do we quantify the pressure, and what is the pressure? What can pressure do? Well, this is something that when you have when you take the when you fly and then in the airplane there, every time it takes off or touch down, and you feel that very uncomfortable feeling inside your ears. And that's because the air pressure outside of your body, inside your body, is changing when the airplane is taking off or landing. So that pressure imbalance causes the eardrum to be either pushed out or pushed in, and that's where the discomfort comes from there. So pressure is related to the air, to the gases there, and in this case, air. Okay. How do we quantify pressure? And we always say chemistry is quantitative science there. So we need to know how do we quantify each of the quantities that we introduce here. Now, the relationship between the amount of substance and the pressure of the gas there, since mass density equals to mass over volume, so mass of the gas would equal to density of the gas times the volume of the gas. Okay. Now, the pressure in physics, we define pressure as force over area. Now, force in physics is defined by mass times gravity. Mass is how much matter you have there. G is the gravitational force, the acceleration due to gravity. On the Earth, we consider that as a constant, although around the equator and around the North Pole and South Pole, their G value is slightly different, but it's not significantly different. It's around 9.8 meters per second. Well, if you go to the moon, that number is only about 1/6 of what we have on the Earth. Okay. So mass times gravity, mass times the acceleration due to gravity, that's how we define force in physics. And mass equals to density times volume. So we can substitute density times volume, we can substitute m with density times volume. So this equation becomes acceleration due to gravity times density times volume divided by area. Now we know volume is defined by the length. Well, when you do a cube, when you have a cube there, okay, and the volume is the length raised to the third power. Area, when you have a square or rectangle shape, area is the length raised to the second power. So if you have ratio between volume and area, well, volume and area, volume would be x to the cube, area would be x to the square. So the ratio between volume and the area would just be cancel out the x squared, and you end up with x. X is the length. Okay. So in this case, and length is the height. Okay. So in this case, we can substitute the ratio between V and A, volume and area, with the height after the cancellation of the x squared there. And so we have pressure of the gas equals to, or pressure of anything in that matter, equals to gravitational force, the acceleration due to gravity, times the density times the height of the column. So if you have a water column or if you have an air column, the height of that column will determine the pressure that can be exerted, can be generated from that quantity there. And G is a constant on Earth. Density, well, density depends on what matter you have. If you have water, density is 1. If you have gold, density is 19.3. Okay? And if you have mercury, density is 13 point something. So density, we can see, what we can say here is that pressure, based on this particular equation there, pressure is directly proportional to the density and the height of the column of the matter there. So, since G is a constant there. Okay? So, the question here is that the old-fashioned barometer, we always use mercury in the barometer. why don't you use something cheaper, non-toxic, like water? There's a question there. When we measure the pressure there, and pressure is being measured, one of the unit that we use there is millimeter mercury, the height of the mercury column there. Okay. Now, the Italian scientist Torricelli, who studied the pressure and came up with a measurement, a device that we can measure the pressure, air pressure there. This is the first barometer. Okay. If you have a glass tubing, you suck the air out of it, it's vacuum inside, and then you put that glass tubing into liquid mercury. Now the air pressure on the outside will push the mercury into the glass tubing. Okay. The height, somewhere around the sea level, the height of that mercury column is about 760 millimeters mercury. This is how we define 1 atm. The 1 atm atmospheric pressure equals to 760 millimeter mercury. We call it 1.4 in honor of his research, Torricelli's research there. So the height of the mercury column equals to 760 millimeters mercury when the pressure equals to what we call 1 atm there. Okay? So the question is, why don't we use water? Why do we use mercury instead of using water? Well, we can do a calculation there. If you use a barometer, the barometer using mercury there, the barometer measurement for the pressure is 755 millimeter mercury. And if you try to substitute mercury with water, how long is that water column is going to be? Well, based on the calculation, the pressure generated by the mercury column should equal to the pressure generated by the water column if you're going to use water. Okay? And so G is a constant, and G cancels out. And density of water is 1 gram per cubic centimeter. Okay. Density of mercury is 13.6 gram per cubic centimeter. Plug in the numbers there. The height of the column for the mercury is 755 millimeter. If you want to convert it into inches and foot there, you can plug in all the conversion factor there. At the end of the calculation there, you see if you use water in that barometer there, the barometer will have to be somewhere around 10 meters, 33 feet long. That's a huge barometer, and that's why we don't use water there. We use a liquid with very high density, high density mercury in this case, 13.6 gram per cubic centimeter, and that's why we use mercury. And of course, mercury is toxic and it tends to evaporate, and when you breathe in mercury vapor, it's toxic. And so every time when there's a mercury thermometer, when there's a barometer breaks, the hazmat team has to come in there and they have to clean up the mercury there. Okay, so that's a side note there. So here you know why we don't use water as the material in the barometer there. So pressure can be measured in different units. It's very important that you pay attention to all these different units there. You don't have to memorize them. That's a good thing. Okay? We will give you the conversion factors there, but you need to know what are the common units that we use for the when we deal with the gas law problems there. So millimeter mercury to atmospheric pressure, we want to use, when we introduce the ideal gas law, PV equals nRT later on, we'll say the pressure has to be an atm. So more than likely when you do the experiment there, when you do the when you do the questions, homework questions there, the